All right, we should be recording now. I believe everybody is here. So we'll go ahead and get started. So, howdy everyone. I'm Liam Brennan. I am the director of the Texas A&M Sounding Rocketry team for the 2023-2024 academic year. And this is our official Spaceport America Cup video flight readiness review. We're going to do our best to keep it within the 20-minute time constraint today. So it'll be pretty fast, but we'll have plenty of time for questions after that. So with that, we'll kick it off with a brief overview of the presentation today. See here if it wants to cooperate with me. There we go. Just a little bit of lag there. Sorry about that. All right. So the overview of our presentation today, we will start off with the dynamics of our competition rocket Telemachus. We'll go into a little bit of depth on the aerodynamics of the rocket, as well as some of the design decisions that we made on things like the nose cone and the fins, as well as give a brief overview of our expected performance in competition. Next, we'll move into the airframe, where we will discuss the structural design of the rocket, as well as some of the fabrication materials and methods that we chose. Then we'll move into the recovery system of the rocket, where we'll discuss our parachute selection, altimeter selection, and the electronics that will allow us to successfully recover this rocket. And lastly, we'll close out with our payloads. We have a CubeSat payload as well as a camera payload on this rocket, and we'll give a brief overview of that. So with that, I will go ahead and hand it off to Dynamics.
Howdy, my name is Jack. I will give a brief overview of, hello. I will give a brief overview of the dynamics of our rocket. Starting with the overall dimensions, we have 128.5 inches of length across the whole rocket. This includes a 26-inch nose cone, as well as 102.5 inches of body tube. That includes an 8-inch conical boat tail. As for the weight, our total weight is 46.7 pounds dry and 63.5 pounds wet. The nose cone we chose is a 20-inch von Karman nose cone with a 6-inch tube section. So there's no shoulder on this nose cone, just a tube section. We chose the von Karman nose cone because it offers great performance and is very common in rocketry. As for the fins, we have 4 clip delta fins with hexagonal airfoils. We chose a clip delta shape because it offers a low area distribution and a sturdy shape. So we'll have a nice and stable rocket. With 4 fins, we increase the stability of our rocket, and we don't compromise the overall surface area and shape, leading to fin flutter problems. Additionally, we have a hexagonal airfoil on these fins to increase our performance, as it is the easiest one to manufacture, and it does not compromise the structural integrity of the fin. For the boat tail, we chose an 8-inch conical boat tail with a 4.02-inch exit diameter. The reason we chose a conical boat tail is because it is a very simple geometry, and in our simulations, we found that different geometries of boat tail did not significantly affect the performance of the rocket. We found that an 8-inch length is around the sweet spot for what we want at this competition. The motor we're using is a Loki M3464 motor, which is 7.6 kilograms or 16.8 pounds, and it offers an average thrust of 3,464 newtons. To simulate the rocket, we looked at the average weather in June at White Sands. As we get closer to the launch date, we will update this and change the simulations to account for new weather. But for now, this is what we're using to simulate the rocket. Using these weather conditions, we found that we will expect a 8.2 mile per hour wind coming from southwest. We put this into Open Rocket, RAS Aero, and our student-developed flight simulator to simulate the rocket. Our student-developed flight simulator includes 6 degrees of freedom, and it simulates many times with multiple Monte Carlo simulations. So this accounts for changes in weather, and for each simulation, it slightly modifies those weather conditions to give us an accurate spread of where it might land. For nominal performance in 8.2 mile per hour wind from southwest, we expect that Open Rocket will simulate to 10,746 feet, RAS Aero to 11,011 feet, and the flight simulator to 10,300 feet. For all these simulations, we found that the Rail exit velocity for a 12-foot rail would be 84 feet per second, and a 17-foot rail would be 106 feet per second. We're looking at nominal stabilities off the rail and a thrust to weight ratio around 14. In the worst case scenario, we might encounter something more like 20-mile-per-hour winds. So coming from southwest with 20-mile-per-hour winds, open rocket simulated to 10,579 feet, grass arrow to 10,786 feet, and the flight simulator to 10,185 feet. Again, we have the same exit velocities, and we still have nominal stabilities, although slightly lower according to open rocket, and the same thrust to weight ratio. Here are graphs comparing our 3 simulation methods for the different wind conditions. This is altitude versus time. The same thing for velocity. The same thing for acceleration. You'll note that the max acceleration is around 16 Gs during ignition. And stability versus time. RAS arrow and open rocket utilize the Rogers modified Barrowman equations, which accounts for wind conditions, and that is why you see the oscillation and stability. The flight simulator uses a more basic method. However, both of these methods show that our rocket is going to have nominal stability, and with a 17-foot rail, we expect that our stability will not be below 1.5 calibers in any acceptable weather conditions, such as 20 miles per hour. Here's a recovery spread for 8.2 mile per hour wind from southwest. Our rocket lands almost exactly where it started. In the worst case, we'll have 20 mile per hour wind from southwest, and this leaves our rocket to drift much further. In a scenario like this, we will angle the launch rail 1 or 2 degrees into the wind to have a less risky and shorter recovery. So if we are going to encounter high winds and risky launch conditions, we're more likely to angle the rocket in 1 or 2 degrees into the wind for launch. This will lower the risk of recovery. Additionally, one more concern is that we have not been able to test launch this rocket to validate the simulations. However, we are still in the process of doing this, and we expect that we will do that soon. So,
okay, quick question here, or just a observation. One of the changes that we have this year is that our pads are going to be movable in terms of both azimuth and elevation, whereas in the past they've been basically at a fixed azimuth. And the reason for that is because we had a couple calls that were a little bit too close last year. And so what we've done is made RSO has made a lot of changes to both change the azimuth based on the wind direction and also the limit the elevation depending on which direction the wind is coming from. You know, you may not get a choice about, you know, where that how much they angle the launch rail for you. That's going to be largely determined by the RSO.
okay. Thank you for letting me know.
Yeah.
I've been involved in some of that, and I've seen the pads that they're working on, and Ken Overton has done over 1 million Monte Carlo simulations
Oh yeah.
on all sorts of wind, and they've got a go no go chart with the angles that the pads need to be for different wind speeds, wind directions. It's pretty much going to be, they're going to set all that up themselves.
Okay, thank you.
Yeah.
So I suppose we'll leave the launch conditions in their hands, but at this point, we do expect a nominal conditions for launch ourselves.
Sure. Yeah, and the other thing, you know, the average wind velocity from the site is a little bit misleading because you're really only going to see winds that low, you know, pretty early in the morning. You know, so if you're out, you know, 0600 to 0900, you might see that, but once we get into the afternoon, you know, then you can pretty much expect 10 to 15 mile an hour winds. You know, I mean, just, you know, that's just the nature of the beast out there.
Yeah. So that-
From what I've heard, they're expecting to have to shut down due to the winds. Got an 18-mile-an-hour shut-off point that it may be 1 or 2 o'clock every day that we get shut down due to the winds.
Yeah, yeah. So depending on the, on the exact where the wind is coming from, if the wind shift, especially if the wind shift out of the north, then launch windows are going to be pretty thin for that. So just we just have to be flexible on that.
Okay, thank you. I'll finish my conclusion and then I'll
Okay.
allow structures to present, and then we can continue discussion. But thank you. So finally, if we use a 17-foot launch rail, we will have a 108 foot per second exit velocity, which is safe according to the rules and regulations. And additionally, according to some basic fin flutter calculations, our fins will not flutter until greater than Mach 3. So we are certainly prepared for that. With that, dynamics is concluded, and I will pass it on to structures.
Okay, thank you.
Thank you, Jeff. Howdy, I'm Megan. I'm the structures presenter here today. So here's a brief high-level overview of the different components of our airframe. Our fiberglass sections start from the nose cone down to where the recovery section is, and then we resume back with carbon fiber from the recovery down to the tail cone. Our nose cone here is fiberglass wet layup. So that's 3 layers of the fiberglass, and then that's attached to a straight section, which is a standard body tube of fiberglass, which is 3 layers of prepreg. Each of the fiberglass standard body tubes are. And then that's attached with 1 layer of wet layup on the inside, down to a coupler, which matches the coupler requirements of 6 inches on either side. So, and then that is also attached with more wet layup fiberglass on the inside. So that'll slot into our main standard fiberglass tube. That's made with fiberglass 3300 resin, which is a high temp resin for all its thermal properties. For our tail cone, similar process, also wet layup, but this one is, it's attached to the very last body tube, which is a carbon fiber tube with another layer of fiberglass. And then that's, here. Yeah. And then for our aft section is very overbuilt. We have struts on the inside, which attach the main outer tube, which is that standard carbon fiber prepreg tube, to an inner fiberglass tube, which holds and houses our motor tube. So our motor. So that for the aft section, our fillet composition for our fins includes Pro Set epoxy and West System 403 and 406 for a filler to make it a bit thicker and easier to handle, as well as carbon black.
Okay, and you're doing through the wall fin attachment there? Is
Yeah.
that what I'm seeing? Okay.
Yes, it's through the wall. So there's fillets on both the inside of the fiberglass red tube, or I guess it'd be silver in this picture, and then also on the outside where the main outer body is. The structural
Okay,
component
thanks.
to the red tube on the inside. I'll pass that off to recovery.
Okay, one quick question before you leave. So your fiberglass boat tail, any concerns about that structural strength of that on landing, that you're gonna bust it or anything like that?
No, I'm pretty sure it'll be all right. It's a pretty thick fiberglass wet layup. We have, I think it was 2.5 layers, or I guess it'd be like 3, but 3 layers of fiberglass on the inside, and then it's attached with a kind of, you see the triangular portion of that that's attached to that tube, that's kind of falling off, and then the 1 layer that it's attached to, the main body tube, is pretty strong, I'd say so. And then we have another layer of Bondo over that, but it's not structural, but it's just for the airframe component. But yeah, I'm pretty confident.
Okay, thank you.
Thank you.
Howdy, my name is Jake, and I will be going over the recovery system for Telemachus. So for Telemachus, we have a dual redundant, dual deployment system with 2 events of separation. The first event of separation happens at apogee, where our drogue parachute comes out. You can see that in this first image here. And then looking at the second image here, this is closer to the ground at about 800 feet when our main parachute comes out led by a pilot chute. And as these images progress, our pilot chute holding our main gets higher and higher to where finally our main comes out, inflates, and then the rocket floats to the ground from there. This is a better diagram so you can see everything that's going on with our recovery system. We have 3 separate, I guess, linkages with our shock cord from our nose cone to our body tube with the recovery bay, and then from that same body tube to our main parachute, as well as from the bottom of the body tube to our whole fin can, also holding our drogue chute. Okay, so for our parachutes, for our main parachute, we are going with the Fruity Shoots Iris Ultra Compact 96-inch. And for our drogue parachute, we are going with the Fruity Shoots Classical Elliptical 30-inch. We expect that for our drogue parachute, after that deployment, that will slow us to a descent rate of approximately 81 feet per second. And then when we get lower to the ground and our main parachute comes out, we're looking at a descent rate of closer to 21 feet per second. Now, in terms of parachute protection, we have we're utilizing Nomex blankets as well as a Fruity Shoots deployment bag. In terms of our hardware we have that we're utilizing here, we have a recovery harness made out of tubular Kevlar, which is rated up to 7,200 pounds. And then we just have the linkages from the nose cone to the piston, and then the main to the piston, as well as the piston to the recovery bay. So the piston isn't actually, there's no hard link to the piston. It's just, we can kind of show you later when we go through our whole rocket. We just have 2 holes through the bulkhead, so it's kind of, it's not an actual attachment point. It's just free to move along that shock cord. And then, yeah, we also have the recovery bay to the fin can. So for all the connection points we're looking at, we're using U-bolts. These are rated up to 2,000 pounds. And we also have mounting plates. And then for a fin can, we are using a swivel that's rated up to 3,000 pounds. And then for all the, I guess, linkages, instead of using quick links, we are using soft links. Soft links are rated a little bit higher, up to 4,000 pounds. And then getting into our electronics that we're looking at for recovery bay, our primary altimeter is the Blue Raven, and our redundant backup altimeter is the Egg Timer Proton. And we also have a telemetry module to go with the Proton, so we're going to be getting live data from the rocket. We also have a featherweight GPS in there, just for tracking, and then we have a camera payload, which we'll get into a little bit later. For the actual ejection system, we have charge wells. So for these charge wells, we kind of did a couple pop tests and decided the size of that the charge wells needed to be, like how long they are, as well as the size of the actual black powder charges. So for our main and our drogue, they're kind of similar. We're going with the 3 gram for the 3 gram black powder charge for the primary, and then for our backup, we have a little bit more at 4 grams. Any questions on that, I guess?
Yeah, just one quick question. Are you using what shear pins for your to hold the electronics bay to the rest of it?
So yeah, our electronics bay is kind of encapsulated inside of the upper body tube. It's gonna be screwed in from the outside. We are using shear pins for our nose cone being held in. But yes.
Okay.
All right, and with that, I'll pass it on to the payload to kind of go over what we're including in the payload. Thank you.
Okay, thanks.
Howdy, I'm Akash, and I'll be covering the CubeSat payload. We are developing a radar payload to collect telemetry on the way up and radar altitude, velocity, and further telemetry data during descent. The radar will transmit while the rocket is under main. It operates from between 5.66 to 5.77 gigahertz at a transmit power that's always under 0.5 watts. Overall, we've tested this radar system, and it's proven that it has the potential to be effective at collecting altitude and velocity data using a pulse Doppler system. We determined that the radar is unlikely to interfere with recovery electronics. There are multiple carbon fiber bulkheads between the radar and the recovery bay, and the antenna itself is very directional. So there's almost no chance of power getting to any other system, then back to the radar itself. Furthermore, we've ensured that we follow all the rules for transmissions, and we've worked with Chris Harris specifically. He's attended our design reviews to ensure that we're following both federal rules with having CAM certifications and also following Ezra design rules. And with that, I'll turn it over to the final section for the camera payload.
Howdy, my name is Jason Rivera, and I will quickly cover the camera payload. So in order to accomplish the objectives laid out in the streaming competition, as well as to get footage for our own personal use, we've chosen two different cameras to go into the camera bay, that being a Foxeer Razor Nano and a GoPro Hero 10 Black Bones edition. The Foxeer Razor Nano was chosen as our live streaming camera because we can use it with a commercial off-the-shelf flights controller in order to transmit both the video and telemetry data by analog transmission, which is good for us because it's incredibly robust and resistant to interference and other failure methods. But for the recording camera, we chose an off-the-shelf GoPro because it's proven it has an incredibly high resolution and data rate. And this specific one is incredibly lightweight, allowing us to make sure that we can for sure hit those altitude targets. In order to receive the video on the ground, we're transmitting it using another COTS 1.3 gigahertz band transmission module, which will be received on the ground with a ground station that utilizes a Yagi antenna to make sure that we can keep a good connection, even with the limited power set out by the rules. All of this is being powered by lithium-ion batteries that should give us about 2 hours of runtime. All this to make sure we stay within the bounds of the rules. That, I'll quickly hand it off to Liam to finish up the presentation.
All right. Thank you, everybody. I believe that concludes the slideshow presentation of this flight readiness review. I'd like to go ahead and open up the floor for questions, if there are any remaining questions or longer questions. Because we did go through that a little bit fast to hit our 20-minute time limit. Now we'd like to hear from you before we go ahead and pan over the rocket and show you all the hardware. So are there any remaining questions on the slideshow?
Not right now. Why don't we go straight to the rocket here, and because we can, be easier to clean up a couple items looking at the rocket.
Absolutely. Sounds good. So I will bring the webcam over there now. It's going to take a little bit of mobility here, so bear with me as I transition over to a second table here. Let's see. All right. Angled up. All right. So this is our competition rocket, Telemachus, and the team behind. Yeah. As far as where to start, would you like us to just kind of walk through the rocket section by section?
Yeah, why don't you start at the nose, and we'll work our way back.
Oh, we can't hear them.
Sorry, can you say that again?
You start at the nose, and we'll work our way back.
Oh, I think the speaker's on my laptop.
Wait, can you, my laptop's on, can you just turn up the volume? There we go.
All right, there we go. We got you. Sorry, what was that?
Yeah, start at the nose.
All right. So this is our fiberglass nose cone. It was designed, developed, and fabricated by us.
Yes.
Just make sure they can.
Sorry about that. All right.
Yeah.
Can you hear us?
Yeah, we can hear you.
Okay, perfect. Okay.
All right, awesome. Yep, so this is our nose cone. It was designed, developed, and fabricated by us. It is primarily made of fiberglass. It's a Von Karman.
20-inch nose cone.
Right.
It was made using a 3D mold. Yeah, on the side.
Okay. So is it, so your payload, your radar payload, is that's contained in the nose cone? Did I understand that correctly?
Yes. Yes, we're gonna pull it out right now.
Okay. And but in flight, the nose cone won't be separating. It'll be
Yeah,
screwed
yeah.
on.
You can take out the. I don't know why. There we go. Okay, yeah, there we go. Okay, so there's shear pin holes right here, and that will go onto the shoulder of the nose cone, and then the payload, as you can see, will go right in here. This is
Okay.
our
The CubeSat
CubeSat.
tightly here, and
Yes.
it just simply slots in. And
It-
the radar is stored inside.
And then we have this oh my god. We have a
Okay.
bulkhead, yes, that is connected, and obviously, as you can see, we have our shock
Okay.
cords that will connect everything. This will all be secured inside the nose cone.
Okay.
And the shock cord will be connected to this body tube, which this middle section will have our recovery bay, and the recovery bay will be secured inside the body tube. And then on the other side, the recovery bay, I guess inside the recovery bay is here. We don't have a board with us currently, but this is a recovery bay. This will go in here. Each side of it. So yeah. And then we have our piston right here. And then this will go inside of our body tube, as you can see right here. This has our camera, the slot. And then this will be connected, this other side, this other U-bolt will be connected to the aft section of the rocket, which to this U-bolt. To the swivel, sorry, to the swivel that's on the U-bolt. Yes. And then you can see this is our aft section.
Okay, so before you go any farther, so what are you planning to do to mount your electronics there?
Yeah, so we have the recovery sled, right?
Yeah.
That's primarily 3D printed, but Jake, you can still.
Yeah, so the recovery sled is 3D printed. It's just gonna slide right into these all threads here. The actual mounting of the electronics onto the bay, we just have little screws to screw them in. We also have like standoffs on there. So we don't really have any concerns with shearing or anything like that with the actual
Okay.
mount.
And what are you what material are you using for your 3D printing?
Oh, we're using PETG.
PETG, okay.
Yeah.
How what orientation are you going to print your bay in?
It was printed just flat on the build surface.
Okay. Okay, yeah, so one thing that depending on that I've seen in the past is that when you print it in that orientation, it's not as strong to the vibrational kind of loads that you would expect to see. So you might want to consider looking at printing it vertically. If that's and just do some have you done any tests just to make sure everything's going to be able to hold together well enough? The reason I ask is because I've done recovery in the past, and more than once I've had a team open up their ab bay and their 3D printed sled all comes out in pieces, because it basically disintegrated during flight. And which would be sheer luck that the rocket actually worked rather than being a lawn dart. So that's the reason I'm a little bit asking you to make sure that you actually vet how you're going to print it, and do a little bit of testing, at least, so that you've got a good feeling that that this is going to be as stronger than just using a plain old piece of fiberglass or whatever.
Yeah. So all the pop tests we've done, we've had all the electronics and everything inside the bay. So
Okay.
as far as the force from like the charge wells goes, it can definitely withstand that. We've done, I think, a total of 5 pop tests. We have done 2 for the main and 3 for the drogue, and it's been totally fine throughout that whole process. We even had some
We did some at south side as well. So
Yeah.
we did.
Oh, you did it.
more.
Oh, okay. Something more than that. Okay.
Yeah.
But yeah, we've done plenty of pop tests, and it seems to withstand that perfectly fine. We haven't had any problems with anything like
Okay.
that. The board itself, I'm very confident in like the structural integrity.
Okay, yeah, it's like I said, I've done this in my own level 3. I used a printed eBay, and but I ended up having to do like some extra reinforcing, because in a test flight, where I had it screwed into the eBay it just all popped out. And so I ended up having to, use standoffs, longer screws, or longer screws, and then put nuts on the backside just to make sure that everything stayed there. So that's why I, just,
Yeah.
lesson
And
learned there.
Oh, sorry.
Yeah,
all of our
continue.
force like goes through the all thread and everything like that. So there's no actual force on the like electronics tray itself.
Yes. Yeah, the force that comes from these both of these bulkheads go through the all threads right here, and they don't
Yeah.
go through the 3D print.
It's really just vibration.
Yes, it would just be the vibration. But again, the print is parallel to the all thread, not like this. Like
Okay.
it wasn't perpendicular to the all thread. So it
Okay.
should withstand. We're confident that it will withstand after going through more than 5 pop tests.
Yeah.
And
Okay.
of 3 grams and 4 grams.
We have a very high infill percentage on the 3D print, and we also
Okay.
use standoffs for many of the electronics. So we've integrated some of the suggestions that you just mentioned previously, but adding extra nuts would definitely be a good step that we could take.
Yeah. Okay. So tell me about your bulkheads. What do you?
They're carbon fiber laminate bulkheads. They've been water jetted out of a piece that we have for the thicker parts, or thicker bulkheads. But yeah, they just kind of slide into the tubes, and then they're secured.
Okay.
Yeah.
You can see these, there's different layers to them, like this, these
Okay.
are epoxied. And then
Right.
the same for these, that's how they're thicker. Yeah. And then,
Okay, good.
They're pretty sturdy.
yes, they're very, very sturdy.
They're a little
Yeah,
overgrown.
well, they look sturdy, so yeah. It's all
And then,
good.
as you can see, the U-bolt goes through it, and there's nuts on each side. And they have electronics, and then obviously the electronic holes for the charges, the ignite,
Okay.
the matches.
Yeah, those were all water jetted out.
Yes.
Okay. Okay, very good. Good. You can keep going.
Okay.
For the app section. So it's worth noting here that the app section has a bit of a unique design. We have these carbon fiber spars here that were water jet out of the same material as the bulkheads. This provides a little bit of extra torsional rigidity, as well as these are directly connected to our motor tube. So we have a fiberglass motor tube inside this section. You can see this kind of red tube here, that's fiberglass. This was purchased commercial off the shelf to make sure that we had exact tolerances with our motor casing. And the load itself is actually primarily transmitted through the thrust ring on the bottom as it's ascending under thrust. And then during recovery loads, the tensile load of the motor is taken primarily here by this threaded rod.
That is attached to the motor casing.
Yes,
on the
this is
motor.
attached to
Right,
the.
yeah,
That's relatively standard, as you all
Yeah.
are familiar. So moving down here to our rail buttons, we have these 1515 rail buttons here. These are commercial off the shelf, purchased from Lock Precision. They're Delrin. So we had some struggles with that earlier in the year, but now we believe we've solved our problem with these better rail buttons.
okay. And how are they attached there? Are they through using into the are they are they just glued on, or do you got something that goes all the way through the tube with say some kind of back to it?
They were screwed into the laminate.
So this laminate rod, it
Ah.
goes through
struts.
the strut. Yeah, the strut goes through the entire rocket.
Ah,
And
okay.
they're on this, and then so they were epoxied on, and then they're screwed on as well.
So they're screwed into that laminate spar. Okay, good.
Exactly.
Yes, awesome. So yeah, moving on to our fins here. I'll let Fernanda talk more on that because she led the design.
So these fins are carbon fiber laminate fins, and they are, how big are they, Jack?
The fins.
Yes.
So the fins were designed to be in a quarter of an inch thick to withstand the loads on them. But the carbon fiber laminate we made them out of is 3/10 inch thick. So when we sanded them down, they ended at around 285 thousandths of an inch thick. So they're very thick.
And they go through the entire like carbon fiber tube, and they reach to inside to the fiberglass tube, and then so they're filleted inside with carbon fiber, and then they're filleted inside, and then we put this carbon fiber tube, and then we also fillet it here, as you can see here, throughout the entire thing, and with the type of epoxies and carbon fiber that we listed before. And then they've been sanded down. Again, you can see the hexagonal shape right here of the airfoil, and all the fins are exactly the same. And then they've been wet laid up with carbon fiber as well.
So just to be clear, we've put tip to tip on both the
Yeah.
motor tube, on the motor tube with the fins.
Yes.
So it's fillets for the fins attaching it to the motor tube, as well as carbon fiber tip to tip.
Okay.
So 2 layers. And then we attach, we 3D made, or we 3D printed a mold that was wet layup with fiberglass for the tail cone. And then we attached it using fiberglass sheets onto the carbon fiber tube. And then we put another sheet of fiberglass and then painted it black, as you can see. And then this is our, can we take this out? Will it come out? Yeah. Anyways, this is our motor retainer. This is our motor retainer. You can see like these nuts right here, and this will make it, because our motor tube is made to hold an O motor, but so we decided to go with a bigger diameter. But this is the motor retainer, and this will hold our M3464 motor.
Okay. Is that a commercial one, or did you make it yourself?
We made it ourselves.
Okay. And it's what's it made of? Aluminum?
Like, are you talking about the very
The
bottom?
retainer itself, yeah.
Yeah. The tube was an excess from the fiberglass, the COTS fiberglass we had on the inside. But then the rest of it is just bought. It was COTS, right?
This was taken from our L2 rocket. So it's kind of a hybrid of a COTS part and a student research and develops part. So it has a COTS actual like motor retainer, and then there's a little bit of fiberglass tube that was added to it with a little bit of epoxy, just to make sure that it slot nice into our boat tail. So It's kind of a combination of the two, to answer your question.
And that COTS part comes from a CTI motor retainer.
Yes.
Okay. Okay, so when you're loading your motor, then you just unscrew that retainer off the back and slide that thing in. That's the plan.
Yes.
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 Okay.
Okay.
Okay, continue.
Or that's the end of the rockets.
So let's move to the payload.
But we
here.
can, yeah, we can.
Akash, if you'd like to break down this was the internals of our CubeSat payload. And then it'll have a kind of external structure similar to that one right there. So Akash,
Okay.
Yeah, I mean, these are radar electronics. I don't know how detailed you'd like me to be, but we have a variety of analog electronic components as well as custom-built PCB that has a pair of accelerometers, one high G, one low G, a magnometer, a gyroscope, and together that is able to collect detailed telemetry data throughout the entire flight, including during launch itself because of the high G accelerometer. And we have the entire radar system here that is able to collect data on descent. We don't have the final payload structure here with us, nor the batteries, both of those. But it's a CubeSat form factor. The majority of it will be aluminum and steel, and the top to ensure transmission will primarily be fiberglass.
Okay. All right, good. So I see, yeah, so you haven't painted so we won't worry about the markings or anything like that. Just make sure I've covered all the pieces in my checklist.
I do have one question about your
Yes,
altimeter
sir.
battery.
Yeah, I
Are
was
they,
fixing to ask that too. Go for it.
yeah, the altimeter batteries, are they what the manufacturer recommends or just lipos?
So for both the altimeters, we have Li-ion batteries. They work perfectly fine with the altimeters. But in terms of GPS, we have a LiPo. It came like with the manufacturer, so I think we're able to use it.
Yes,
and for
that's
the rules.
correct. Yeah.
But yeah.
Yeah,
Okay.
there's for the altimeters, it's I guess it's going to be required that you use lipos that are recommended by the manufacturer.
Yeah.
Not just any lipos, but ones that either come from the manufacturer or the manufacturer recommends.
Okay.
Yeah, right. And actually, we would prefer not to use lipos at all. So what you've got already is just fine. But we're given the exception to use lipos if that's what the manufacturer recommends or supplies with a piece of hardware. That's how the rule is structured.
Okay. Yeah. Perfect.
Okay. Harry, do you got any comments you'd like to make or any questions you'd like to ask the team before I kind of go through my in-game stuff?
No, everything looks pretty good to me.
Yeah. No, agreed. Okay, so couple questions. First, do you have possession of your motor yet?
Yes, so we actually have possession of 4 motors. So we made
okay.
Just so we were looking to get in 3 test launches before competition. So unfortunately, the weather hasn't worked out for us.
Yeah, no kidding. Yeah.
Yeah.
So the rocket was built around the motors. We bought them back in August, so we wanted to make sure we have them in our possessions before we made any critical design decisions. So we bought them and then we basically built our rocket behind it. And so yes, we have all 4 motors and we've prepped one already and we were gonna use it this weekend. Yes.
Okay, good. Good. be interesting to see how the results of that. Yeah, and so I take it y'all are not gonna ship anything, you're just gonna schlep everything over from College Station to here?
Yes, sir.
Okay, good, so I'll skip that part. Just okay, first, thank you for the video review. Like Harry said, this all looks good to me. I think you've got a solid rocket, and there's some good design and some good thought behind it. So I think that it's looking really good from my aspect here. So just a couple of things I just want to foot stomp to make sure everybody gets understands. Y'all going to be responsible for your own, food and water during the event. I mean, there'll be a water buffalo out there, but I would suggest bring your own. You got the transportation's already done, shipping's in A. Make sure you bring chairs for your team. There will be tents and tables provided in the team area, so you don't have to bring shelters or anything like that unless you really want to. How many of you have been out to the spaceport before?
I have, I believe.
Two of our members here have.
Okay, so enough of you, so I don't have to really brief you about the conditions. But yeah, it's gonna be, bloody hot out there. I highly encourage long sleeve shirts, big floppy hats. I've got I'll be wearing a long sleeve fishing shirt, which actually works really good for the temperature out there, just to keep it. But plus I've had so many skin cancers carved off me, I really gotta watch myself nowadays. But yeah, so but make sure you bring some good clothes that you can cover up with. You do not want to get sunburned bad early in the competition, because it'll be pretty darn miserable. So hats, sunglasses, sunscreen. You've got your own travel arrangements. Do you have a place you're going to stay yet?
Yeah, we have booked a hotel in Las Cruces. It's actually the same one we stayed at 2 years ago, so we're looking forward.
Okay. So needless to say, don't do any final painting or, epoxying in your hotel rooms before the contest, because we've had occasional problems. We've been having to, smooth the waters when teams got sloppy. Actually, this is one reason why we're having the review out a month prior, just so that so that we got a good feel that your rocket is pretty well built, pretty well there, and that you're not going to be the night before competition gluing your fins on. That has been done, and it's usually not good. Okay, we already talked about the ham license, and several of you are AAA certified and are members. Is that correct?
Yes.
Yeah, I think we have
Okay.
3 L2 certified members and several more L1 certified members attending.
Okay. Okay, really good. Do you have any questions for me?
I do not. Do any of y'all?
I just have a quick question.
Yes,
I know
sir.
I know in the website for the streaming competition, it talks about there being, I don't remember exactly what model it is, but there's a little auxiliary, let me get in frame. Yeah, there's a little auxiliary, it's like a handheld unit that they're using to coordinate the live streams. I'm just curious if you can give us any more insight onto the situation with that. I know that we sent in something. We said we could do 1080p with an HDMI cable out of a computer. We can still do that. I'm just curious because it's not the most clear on the website to me.
Yeah, and unfortunately, that's not something I'm smart on. But I'll have to defer that to Logan Herrera, who's the guy running the live stream. Actually, you guys have got my email, drbillhanson@gmail.com. Send me a note on that and I'll forward it to Logan to try to get you a definitive answer on that.
Sure. That's all good.
Okay.
Thank you.
I'm on the live stream Slack
Ah.
channel, which they are still trying to figure out the best way to use some of that stuff. I can ask on there and maybe
Okay,
have
yeah.
an answer for them this weekend.
Yeah, okay. Well, why don't you do that then, Harry? That's if you're already there up in that channel. I mean, I do read it, but it's kind of since I'm concentrating on the recovery data collection, that's I'm not paying a lot of attention to that.
Yeah, I'm looking at it. I know they're still trying to piece everything together and getting all the parts around and what's going to work and not work. So they may not know for sure yet themselves, but I'll see what I can find out.
Okay, thank you very much, Harry. Anybody else have anything they want to add?
No, but if we're gonna go ahead and conclude, I just want to thank you all so much for your time and your expertise. Harry, we really appreciated your mentorship this year, and we're really excited to launch this rocket this weekend and put the finishing touches on it and hopefully achieve a really great result at competition. So we're really excited for the next month or so, and thank you both for being a part of that. So
Yeah, you're sure welcome,
Well-
and glad to do it. You guys, you all, ladies and gentlemen, you've done a good job with your presentation. And like I said, you've made solid design choices on your rocket. Everything's looking good from where I stand, and so you'll definitely get an up check from me. And so make sure that you send the shareable link of your video to general info at EsraRocket.org, and just to make sure that we got that.
absolutely will do. We'll finish up all of our competition documentation with the technical report and the video and all that here in the next day or so. So we'll be sure to do that.
Okay, very good. Okay, any last minute thing anybody want to say? All right,
Pretty
and
good.
team, thank you very much for your time and effort, and I'm looking forward to seeing you in a month.
Yes.
Yep, we'll see you there.
We're very
And
excited.
I'll see you all Saturday morning, and hopefully the weather will be good and you'll get it in the air.
Yes.
Yep, knock on wood.
Yeah,
I know,
roger
yeah.
that, yeah.
It looks really good right now, so we're very excited.
Okay, well, thanks so much, and you all have a great rest of the day.
Thank
You
you.
too.
You
Bye.
too. Bye-bye.
Okay, bye-bye.
Bye.